find the equation of the line tangent to the surface of z equals 25 minus x squared minus y squared on the x equals 1 trace. Okay, so this looks like a really, really hard problem. Let's just see if we can kind of understand what it means. First thing I'd like you to do is convert this equation to cylindrical for me. Okay? Convert this to cylindrical so you can understand this problem a little better. Do that. This is like a warm-up. Just so you can understand it better and maybe even visualize the graph. You could make up x's and y's if you want to try to plot this thing, but I think you're better off just converting this to z equals 25 minus x squared plus y squared. In other words, z equals 25 minus r squared. Right? I mean, now you're just basically, you have two variables. You get to make up whichever variable you want. Question? I factored out the negative.
Could you also just multiply everything by negative and then make it r squared plus z equals negative 25?
Sure. R squared plus z equals negative 25. You mean r squared plus z equals 25?
Yeah.
Yeah, bring the variables to the left. Sure, you can do that. Okay, so actually I think what I'm going to do is make up some z's. I think it'll help me understand this. Okay, so let's make up some z's, and then we'll figure out what r's are, and we'll try to kind of sketch this out. Or you could do it the other way around. Okay, I'm going to make up some z's. Why don't we make z 0? And this now reads 0 equals 25 minus r squared. Okay, so what is r? 5. Okay. Let's go ahead and make z equal to, I don't know, 3 maybe? Or how about, let's make it 4. Doesn't matter really. 4 equals 25 minus r squared. R squared is 21. Alright, so that's like square root of 21. It's about 4.6, roughly. Okay, let's make maybe z8. I have no particular reason for picking 8. I'm just trying to get a few points. Make it 9? Sure. Let's make that 9. Yeah, that works out real good, because then we have r squared equals 16. So basically r is 4. And you can go as high as you want. You can make z, you know, if you want to make z 25, you could. Let's make z 16. See what happens there. Z is 16. You get r squared equals 9. So basically r is 3. This is probably enough. I'm going to do one more. I'm going to make z 25. So now I have 25 equals 25 minus r squared, so r is 0. And I want to draw it. It is not necessary to draw, okay, in this kind of stuff, but when you're learning the meaning of things, you probably need to see a drawing of a thing. Okay, I'm going to make the x-axis come outwards at me, and the y-axis go to the right. And I've got lots of points to think about. When z is literally 0, r is 5. So right here on the xy plane, maybe we should mark off our axes. This is 5, and this is 5, and this is negative 5, and this is negative 5. And just kind of mark out a circle. It's a radius 5 circle, you see. You have to make it look a little bit like an oval to give it some perspective. Okay, and that's your base. I guess you could treat it kind of like a base of a solid. If the xy plane is your desk, that's right on the desk. Okay. Okay, if you go up to z equals 4, the radius has shrunk a little. Not much. The radius drops from 5 to 4.6, right? So you'll lose a little radius when you go up 4 full spaces. Okay? So maybe draw another ring above this one. So up 2, 3, 4, draw a smaller ring. And then we're going to go up to 9, 5, 6, 7, 8, 9, and then draw a smaller ring still. Just trying to give you some idea of what it looks like. And if you go all the way up to 16, you're down to radius 3. Really, the radius isn't diminishing that quickly. It's gone from 5 to 4.6, now it's at 4, now it's going to 3. But you've gone up quite a bit on the z-axis, and this circle is just slowly losing radius. So we're all the way up at 16, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Now you finally got a radius 3 circle. And when you get up to 25, the circle has radius 0. So I think what's going on is it looks something like this. If the graph on your worksheet is a sombrero with a wavy look, this is more like a dunce cap. Okay? Now, here's a question. Is this more like a cone, or is it more like a ball? You know, if you saw the movie Interstellar, in the beginning there's, well, throughout the movie there's these sandstorms that come through, and people are putting their bowls upside down on the table to keep the dirt out of them. And that's just what they would do during the day. The bowls were always on the table upside down. So this is either an upside down bowl or it's an upside down cone. Like, which is it? How can you tell? Well, one thing you might want to do is just slice it. And however it looks when you slice it, you know, it'll help you decide are the edges on this thing straight or not straight, right? So that's very easy to do. In fact, I'm asking you to slice. What does it mean to find the x equals 1 trace anyway? What does this mean, the x equals 1 trace? It means pretend that x equals 1 plane is like a blade slicing down. So right out here. Slices right through x equals 1. Okay? So the x equals 1 trace would be if you took x equals 1, which is this line. Okay? Pretend this is a big blade. And it's slicing right through your bowl. When it hits that bowl, what does the cut look like, you know? Is it a parabola type slice off the edge, or is it more of a cone, like a triangle? If it's a triangle, it's probably a cone. If this slice is rounded, you know, on the edges, then it's more like a parabola type of look. Does that make sense? So how do you slice? You just plug in x equals 1. You ask yourself, what curve? This ball-shaped thing is made up of many, many curves. When x is 1, what does the curve look like? Well, let's plug in 1 for x. What does it look like? If I plug in 1 for x, what do I get? Z equals 25 minus 1 minus y squared. Z is 24 minus y squared. What is that? What kind of shape has one variable squared and one variable not squared? A parabola. Right. So evidently, this edge here, which I found just by making this one, this red thing must be a parabola. You can tell from its equation, you see. So I'm pretty sure that this is a cone, right? Like, it's kind of like a cone thing, but I think it's kind of rounded on top. If you really want to be sure, you know, you can also plug in x equals 0, and you get 25 minus 1. So like this up here is also a parabola. In fact, there are many, many, many parabolas here. Okay? Many parabolas. I'll draw a couple more. Let's use green. So you could go right up over the top of this if you make x 0. The red one is when x is 1. So this is the x equals 0 trace. Spell that wrong. This is the x equals 1 trace. See? And there are many traces. It just depends on where you want to slice. So what is a trace? The trace is the image you get when you slice a plane through a curve. And some people like to call the x equals 0 trace the YZ trace, because that's where the y and z axes form a plane. did I give you coordinates? I need to give you a point. At 1, comma 2. At 1, comma 2. I forgot to write that. So where is 1, comma 2? When x is 1, y is 2. Well, if x is 1 and y is 2, what's the z value? If x is 1 and y is 2, what's the z value? How'd you get that? Yeah, when x is 1 and y is 2, z would naturally be 20. So I'll make the question a little more obvious by putting what is the equation line tangent to the trace, the x equals 1 trace, at 1, 2, 20. So we're talking specifically about this point, 1, 2, 20. That's the point 1, 2, 20. Okay, so now you kind of understand the problem. We're asking for this line. You see. But what do we call it when you hold x as a constant and you find the slope of the curve? The partial derivative with respect to y. So we're at a constant x. Let me scroll down a little so you can see my labels. Look at your axis that's labeled. You're at a constant x. That's this red thing. You wish to find a slope. That's dz dy. That's dz dy. The slope of that line is dz dy. You guys agree? Okay, cool. So we get the slope of the line using dz dy. That's half the battle. Okay, so the slope of this thing is going to be dz dy, and of course you're going to plug in the 1, 2, 20, because you don't want just any slope, you want the slope at that point. Okay, so the slope of that line is dz dy. Partial derivatives are easy to find. Then we'll plug in 1, 2, and 20, we'll have the slope of that line. Okay, let me go ahead and clear out some of this old work. This was just so we could kind of see the sketch. We converted to cylindrical. We drew a little table. You'll get so good at that, you will never need to do that again. Okay, so all the rest of my work will be in purple because that's what I'm finding is that purple line. So what is the equation of the line? Well, the slope is going to be dz dy. We don't really use the word slope in 3D, but since we've already drawn a trace, right, I mean, we're kind of bringing this back to 2 dimensions now. We've got the plane, so we're kind of doing slope on a plane. What's the question? That's given. I meant to write at the beginning, but I didn't. So when the time arose, I put it in, sorry. Okay, so dz dy, you guys know how to find the partial derivative. It's pretty easy, right? Okay, so what's the derivative? You're treating, basically x as a constant. Treat x as a constant, what's the derivative of this thing? Yeah, negative 2y, right. All right. If the top here, dz, if z is actually isolated, then you don't need to change it at all. It's only when the z is very on the right side also. That's when you convert it. So just treat x as constant. After all, we are talking about this constant x slice, right? Okay. And then we're going to plug in. Well, we're supposed to plug in, 1, 2, and 20, but we're only going to be able to plug in the 2, right? Okay. So what is the slope? Negative 4. Please express that as a fraction. So how would you express negative 4 as a fraction? Negative 16 over 4. Okay. Negative 16 over 4, or just negative 4 over 1, right? So remember, when you're trying to find the equation of a line in 3 space, you're supposed to use this rule, remember? You're supposed to use, well, do you guys remember it? R of t equals, what's the equation of a line? It's been a couple days here. X naught, Y naught, Z naught, I heard someone say. Plus T ABC. And if you've been struggling with what A, B, and C means those really just represent delta x, delta y, delta z. Or as the Aussies say, delta z. Okay? That's all they represent. But looking at this picture, I'm really glad we drew the picture for our first one here. You can see that dz dy was negative 4. I had you write it as fractional purpose. You can treat this as your delta z, negative 4. And you can treat the 1 as your delta y, z. So we can steal the 4 and the 1 and put it in here for our c and our b. The slope is dz over dy on the curve, but since the line is actually a straight line, you can change these back to deltas now. So these are actually just regular delta z, delta y. So you can steal those and put them in. You can either put the negative 4 here and a positive 1 for b, or you can make the 1 the negative and make the 4 positive. It doesn't really matter. There's a lot of forgiveness here because t can be anything anyway. So we're basically going to write this, you see, as 4 and negative 1, or you can do positive 1 and negative 4. It doesn't make any difference. So we're almost done. What is the A value? What is the delta x? Well, this line is on an x equals 1 trace. It never changes its x, right? So this is just 0. The change in x is 0. It doesn't come out of this plane. See, it's stuck on that plane. So this is 0 here. And x naught, y naught, z naught, that's easy. That's just the position vector for any point you happen to know. Well, the point we know is 1, 2, 20. So that's going to be our x naught, y naught, z naught, and we did it. We got the equation of a line tangent to a trace. Okay, so this is 1, 2, 20, and that's the answer. Now you could put it into symmetric form or parametric form, but let's just leave it. As we saw before, the symmetric form doesn't even always work, you know? You can't even always do it, so let's just leave it like that. If you want to put it into one vector, you can do that. So you can have one set of brackets, and then you just do 1 plus 0t, and 2 plus negative 1t, 20 plus 4t. So some people like to clean it up a little, you know. So now they have 1 plus 0t, 2 minus 1t, 20 plus 4t. Some people like to write it like that. I actually don't care much for that. I like keeping these separate because I like to, if I ever want to replot it, I know exactly where to start. I'm going to start at 1 to 20, and I'm going to use this kind of as my slope. This 0 to 20, negative 1, 4. And I want to remind you, it doesn't matter if you make the 1 negative or the 4 negative. Just choose one because t is going to be negative 1 eventually anyway, so it won't make any difference.
So you knew to make it dz dy because you already knew that it was at x equals 1.
X was constant, right? So finding the slope when x is constant is the same thing as finding partial
So if
derivative
it said
of
on
y.
if it said like on the y equals 1 trace, you would do
I would have done dz dx. Yeah. Excellent. Good. Okay, any questions on that example? So here's how we can tie in what we learned 2 weeks, or a week and a half ago, and what we just learned. We were able to find the slope on a trace by using a partial derivative. So a trace is just a slice of the full conic, or the full solid. Okay? All right, and then our main objective today, though, is not to review how we can link old and new problems. Our main objective today is to talk about that hiker again and give him the option of traveling in any direction he wants. Because so far we've restricted that guy to travel either north or south, east or west. In other words, he has these traces here, these red planes have to be parallel to an axis, and that's just too restrictive. So we need to let him have the freedom to hike in other directions. Who says you're going to travel strictly east, west, or north, south, right? How's that working for you? Yeah? It's pretty cool. She's using an iPad with a stylus to take notes. Are you using penultimate? Good notes? That's nice. And you can shrink them and move them off to the side, right? Yeah, I can actually shrink stuff too than this thing. This is kind of fun. Okay. So I know this is really, really an ugly graph. I'm just not that good at it. Sydney will have to help you with your art skills. Okay? After she decorates my room. Okay? Okay. I just have to give you the main idea. And next time you wouldn't really need to draw anything. Or maybe the next 5 problems you'll have to, and then after that you can stop drawing, you know. Okay. So last time we talked about our little hiker guy, and we restricted the hiker to travel either east-west or north-south, meaning either along the x direction or the y direction. And z would change as he hiked, or she hiked, right? So let's give that hiker some more freedom to travel in any direction they choose. How does that work? Okay, so let's fill in our blanks first, and we'll get into the example pretty quick, actually. Okay, now we move on to what's called directional derivatives. In the last section, we only studied the rate of change of z as x changed or as y changed. Okay, so you were only allowed to go in the x direction or the y direction. You couldn't do both. And we call these partial derivatives, and we denote them dz, dx, dz, dy, with the curly d. And finding the rate of change in a direction that is a combination of x and y is called finding a directional derivative. So this is our goal, our objective for today. It's called finding a directional derivative. Now, before you think that this stuff is so way beyond you and you'll never use it, know that 2 students walked in this morning wanting to ask me today, one of their goals today was to come ask Mr. Shore what is a directional derivative. Because they opened the physics book and there it was. So they came in today and I handed them notes and they said, that's so weird, Mr. Shore. I was just going to ask you today what is a directional derivative. The physics book demands they know it. Evidently. Same thing. Okay. We need a new tool, okay? And that's vectors. It's not a new tool, but it's the only tool we can really use here that I know of that's an efficient enough tool. And so to achieve this directional derivative idea, we need to determine how well our partial derivatives align with our desired direction of travel. Okay? We start by defining a brand new vector called the gradient of f, or simply grad f. Grad f. This little upside down triangle, I have it in a bold font, okay? And that's because I was too lazy to put the vector hat on top. You can write it one of 3 ways, folks. You can write it like this, grad f, or grad f with the hat all the way across the top. Or you can leave it bold, if you can write it sort of bold. In physics books and math books, often they'll just make it bold because the hat honestly is kind of hard to find in the font menu. So you have to know where it is. It's under accents if you use Microsoft Equation Editor. And so anyway, what is grad f? What is that thing? Grad f is just a vector made up of our partial derivatives. So it's literally just df dx, comma, df dy. Or you could say it's f sub x, comma, f sub y. You know, same thing. Now this is for a hiker traveling on a surface, a hill, you know. He's traveling along this surface and he can either go x or y or both, like a hybrid function. You could also do this in 3D. It's a little bit hard to understand because it's not a hiker anymore. It's maybe a bumblebee flying through a room, okay? So the hiker doesn't have the option of leaving the surface he's walking on, okay? So bear with me for just a second. The reason I'm not showing my work for this is a little more complicated to understand. In 3D, you have the hiker, or in the surface example, you have the hiker traveling along the surface. He's bound to the surface. He can't get off the surface, right? He can travel only on the surface. Z changes and it's not his fault. If he df dx, df dy, and df dz, but I think it's too complicated for today. At least since I plan on explaining everything using that hiker. Okay, so we're going to just use the first one over there, df dx, df dy. But just know that if you want to do it 3D, it's not any harder mathematically, but it's a little bit harder to grasp the meaning. Okay, so how do you find du, the directional derivative? Well, you're going to find the dot product. Here's the rule of the day. You're going to find the dot product of this gradient vector, evaluated, of course, at some point of interest, and the unit vector for your desired direction. It's a dot product today, okay? So before we do anything else, let's make sure that everybody who was not in physics this year knows how to find a dot product. So if you have two vectors, A, B, and C, D, and you want to dot them together, you just take AC plus BD. The result is a number. You just get a single number. Done. Raise your hand if you were not in physics. Okay. Dot product is very simple. It is the objective of every problem here, so we want to make sure we know exactly what to do when we get to the end. We're going to be doing this at the end. Okay, now let's do our first example. Okay, find the directional derivative du at the point 2, 0 for fxy equals x squared e to the xy plus yx, where u is the vector in the direction of theta equals 4 pi over 3. Uh-oh. So what do we got to do here? Dot product. We need to do a dot product. What are we dotting? The grad f vector dotted with u. U means the unit vector in desired direction. Okay? Grad f is just partial derivatives. Notice there's no z's on the right side of this function. There literally are only two independent variables, x and y. This is the hiker, not the bumblebee. Okay? All right. Do you guys want to find the unit vector for the desired direction first, or do you guys want to find grad f first? It doesn't matter to me. You need both anyway.
Grad f.
Let's do grad f. So we're going to skip down here to where it says meanwhile. Okay? We just did partial derivatives. Shouldn't be very hard. Your function, let me write it right here so we can see it nice and clear. It's z equals x squared e to the xy plus yx. You're going to be treating, first time through, you're going to be treating x as your variable, y as a number. Okay? Okay, so it looks to me like we're going to have to break this up a little bit. That's, I just copied it from up here. Too hard to read? Okay, I think I'll write it one more time anyway, because I need to really think about this. How am I going to treat y like a number, you know? Why don't we treat this as like u, and this is like v. Okay, so we need product rule. So we're finding df dx first. Let's see, u prime v plus uv prime. V prime is going to be y e to the xy. Plus, and then we have this yx. But y is a number, so you might have to think of it as 5x. But I think the derivative of that is just y. Okay, that was df dx. Don't worry, we're planning on plugging in numbers in a minute, so this will all be real nice and tidy. Now time for df dy, the partial derivative with respect to y. So now we're doing df dy. I think I'm going to look at it a little bit differently this time. since x is now going to be treated as a number, I don't think I need to stress out about this x squared at all. The derivative is just going to be y x squared e to the xy. So if you don't believe me, you can make your x like into a pi or whatever. Just make it like this, pi squared e to the pi y, and say what's the derivative? It's going to be pi cubed e to the pi y. Right? We're d-dy-ing this now. So this would be pi cubed e to the pi y. So it's x cubed e to the xy. So x cubed e to the xy plus, and then just simply x, because we're treating x as a number, and it's sort of a slope on that y. So hopefully you're comfortable with that. But that's your grad f vector. Let's go ahead and plug in our numbers, because it's not enough to find the grad vector. You've got to do it at the point 2, 0, see? So let's plug in the numbers. Now this is assumed that this is x and y. They didn't give us the z. Why do you suppose they didn't give us the z coordinate? There is a z. It would be found by plugging, this is like z equals x squared e to x. Because it isn't necessary. Right? The hiker can't control his z. You guys understand? Hiker controls his x and y. Right? The z is dictated by the hill. He can't control it. So they just don't give the z every time. Sometimes they do, sometimes they don't. But these are clearly an x and a y. Also, you don't really need z to solve this. Let's go ahead and plug in the 2 and the 0. And this is just going to all clean up real nice. All the y's are zeros. So this is just going to become 4 e to the 0 plus 4 times 0. So this first component, even the last y there, 0, is just 4. In fact, the answer to this problem is 410. That's the answer, 4 comma 10. Okay, so what is this thing? What exactly is 410? It's grad f. What does it mean for the hiker? We'll talk about it at the end of the problem, okay? Because our objective was not to study every detail as we went. Our goal was to get the answer. We'll go back and we'll talk about what all these ingredients mean. Okay, so we just got our first of two things. You guys wanted to do that first. We also need to go up a line here. We were supposed to find the unit vector in the direction of 4 pi over 3. How many of you know the unit circle pretty well? 2 of you. You just took the BC CALC exam. Glad you know the unit circle. Didn't? Okay. Well, you have to understand that a unit vector is a vector that's 1 unit long. So you can actually use the unit circle to get unit vectors. 4 pi over 3 represents the 240 degree direction, right? 240 degree direction has coordinates, remember, negative half, negative root 3 over 2. So if you're looking for a position vector that's 1 unit long, pointing exactly in this direction, why not just use negative 1 half, negative root 3 over 2? That's the end of that. Finding u is just finding cos 240, sine 240. See, cos 240, sine 240. That's a unit vector. You can check its magnitude if you don't believe me, but if you square these and add it, you get 1/4 plus 3/4, which is 1. So the magnitude is clearly 1. Unit vector can be stolen from the unit circle coordinate. It's very simple. Hopefully they give us data every time like that. That's very nice. So our 2 ingredients of this problem were the unit vector in the desired direction and the grad f vector. What were we supposed to do with these 2 things? Dot them. Dot them. Okay? Oh, I was supposed to put my 410 on this line. Sorry about that. Okay, so we're going to dot 410 and negative half, negative root 3 over 2. Okay, so here's our final answer. The directional derivative is 410 dotted with negative 1 half, negative root 3 over 2. How do you do a dot product again? Multiply and add, right. So we're going to multiply the x's together, which gives me negative 2. Multiply the y's together, which gives me negative 5 root 3. And if you want to use a calculator, you can get real accurate. I think it's close to negative 10 and a half. I'm going to go ahead and double check that number. So negative 2 minus 5 root 3. It's negative 10.660. Okay, we actually did it. We found du. This is the derivative, the directional derivative at the point 2, 0 for this hiker. Now, what the heck does it mean? Yeah, let's go back. Let's go to the bottom. Okay, and I'm going to show you in this little picture what 2 comma 0 means, what 4 comma 10 means. I'm going to show you what negative 10.66 means, blah, blah, blah. Okay? So, I got this graph. I have to give credit to my sources here since I'm recording. So, I got this graph, this website. I got it from this website. I just basically Googled free online 3D plotter, and this came up. So this is the web link at the top, and I just typed in my function. And it took me a couple tries to get the window right. You know, I had to play around with these x min, x max, and sometimes you don't see anything because honestly, the plotter's doing a lot of work to get these beautiful graphs, and you really have to kind of give it a perfect window to even see anything. But that's just pretty standard. But you can kind of rotate it around. So it's kind of like a wave, you know. It has some flatter regions. So as I turn it around, you can kind of just look at it. Kind of see what it looks like. Okay, kind of like a big ramp. Okay, so let's go back to our notes now. Where are we at? Right here. Please understand that this is x equals 0 right here. And this is x equals 3 right here. You should label that, okay? This is also y equals 0, and this is y equals 3 over here. And the z ranges from about 0 to 80. It took me a while to figure that out, okay? But the z isn't that important. We're trying to find the hiker. Where's the hiker on this horrible rock wall? Okay? He's mountain climbing for the day. He's out there somewhere. He's at 2, 0. 2, 0. So where's 2, 0? Can you find him? Where's our hiker? X is 2, y is 0. Where do you think our hiker is? Right there. Okay. So if this is 1, 2, 3, he's probably, yeah, right here. That's what you said? Okay, can you guys see it? Right there? That's where he's at. He's 2, 0. So 2 in the x direction, no distance in the y direction. But he's on the surface of the hill. So go ahead and go up to the actual surface there. No, that's going up means z, right? Y is this direction. Yep. So 2, 0 is z is dictated by the curve. If you want to know how high off the ground he is, like his elevation, you have to plug in 2 and 0 into the original function. But I don't really need it. My guess is he's about 10 space over. Okay, please listen very, very carefully. I told you I would tell you what all those numbers meant. Okay? Let's talk first about what the 410 means. What was that? We found, grad f. This was at 2, 0. We found grad f, and we got 410. Certainly this has meaning. Okay? Listen what it means. 410 is a vector. It points strictly horizontally. So it's pointing level, like it's not pointing up into the sky. If this is a mountain face, it points either east, south, northwest. It kind of points northeast. Okay? You can think of this as your east and your north. X is like east, y is north. So it's pointing in the direction 410. So it's kind of pointing into the plane, into the hillside. Okay? This is the direction 410. It's a relatively long vector. It's actually quite long. This vector is the direction, listen, that the hiker would take if he wished to take the steepest possible path up the hill. So say that again. That blue arrow represents the steepest possible hill he could climb. There are many directions he could go. If he goes in that direction, he's got the steepest climb possible. Okay? Obviously, most hikers would choose the steepest climb possible, right? Unless they want to get to the top quickly. The steepest way is the fastest way. But that is what this means. Grad F will give you the steepest possible path. How steep is it? Find the magnitude. So you just basically find the magnitude of this vector at 2, 0. In other words, you just do 4 squared plus 10 squared square root. And I think it's around 10.6. Let me check that real quick. Square root of, what is it? No, it's not the same number as last time. Square root of 116. It's 10.77, okay? And if you want the angle, the theta, you know, you could just do inverse tan 10 over 4. And it comes out to about 68 point something degrees. Let me check here. Inverse tan 10 over 4. And my calculator is in radian mode, so let me multiply by 180 over pi. It's 68.199 degrees. What does it mean? If the hiker, for some reason, wants to take the steepest possible path, then he is going to need to go in the 68-degree direction. Okay? And the steepness, the change in z, if he takes that path, will be 10.77. It's the steepest slope around. Okay? Any questions? Okay, at the instant that he's standing on this hillside, he is also standing on this line. This is a very important line. Watch close. He's standing on this line here. Okay, can you see that green line I just drew? That is called a level curve. A level curve. If you slice horizontally through the mountain this way, parallel to the ocean, you know, it gives you this particular curve. This is called a level curve. Okay? The path of steepest ascent, the blue arrow, is perpendicular to the level curve that he's standing on. Okay? So what I'm saying is, if you're on a hill, right, like this, let's make a simpler drawing. You're on a hill, and you are standing right here. Your steepest path is probably that way, you know, towards the mound, right, peak. And, listen, it is perpendicular to this slice, the z equals k's trace that you are currently standing on. So maybe you've been on a mountain before where there's like these little trails going around the mountain. If you keep hiking up, I mean, you get to the top, look around and around and around all the way to the top, or you've driven on a road like that. Okay? Those ones have a little rise to them, but these perfectly horizontal ones that look like lines of latitude on the earth, those are called level curves, and the path of steepest ascent is always perpendicular to that level curve. That's a right angle right there. It makes perfect sense if you think about it. If you're on one of those rings, you would want to go straight to the top and be perpendicular. Okay? So grad F, we haven't even talked about our answer, 10.66. Okay? But the grad F had size 410, that's its vector. He represents the steepest possible climb. That steepness is 10.77. It is in the direction 68. And if I were the hiker, it would be the last direction I wanted to go. Because I want to go the steepest possible way. It's hard for me. Is everyone with me so far? Yeah. It is also perpendicular to that green thing. What's that green thing called? Let's label it. The level curve. The level curve. It's level because, well, it's a constant sea level, you know. You've seen level curves on topographical maps before. Like you've probably seen a topographical map with a mountain on it. It's got those little rings on it. Those are contour lines or level curves. Let's also label it contour lines. The perfect analogy is latitude lines on the surface of the globe. That's the one I'm most familiar with. Okay, but that doesn't answer our question. What was the 10.66? And what was it negative? Right? Didn't we get an answer to this problem? Wasn't it like what was our answer? du equals, what was it? Negative 10 point what? 660. What is that? What's that thing? Well, you see, the hiker in this problem was wanting to go in the direction of 240 degrees. That was actually given in this problem. So which direction is 240, do you think? Yeah, so if this is 0 degrees here, and this is 90 degrees here, and this is 180 degrees here, and this is 270 degrees here, I just added some things to my picture. The hiker was intending to travel in the direction 240. Now, of course, relative to where he stands. Right? So I'm going to draw another blue arrow. The hiker was going to actually go this way. You see? It's not the exact opposite of grad F. Grad F was 68 degrees. He's going in the 240 direction. Can you see that he's going downhill? If he does that? Can you understand what this means? Yes, this is the downhill slope for his desired direction of travel. He was going to travel the direction 240, remember? He's going to be going downhill, and it's going to be the steepness. Until he takes his first step, listen, after he takes his first step, everything changes. The grad F changes, the directional derivative changes. So for every spot on the mountain, there's a grad F. For every spot on the hiker's travel, there's a grad F. You understand? Yeah. So what would be a really hard problem is to ask what is the equation of the path the hiker would take to get quickest to the bottom. That's a complicated question because his grad F is always going to change as he goes. Every step, grad F changes, directional derivative, that's the fastest path down changes. Well, the 240 was a given on this problem. And the hiker made that up, right? The hiker's decision was to go in the 240 direction. So the blue arrow kind of went off to the left is the path of steepest descent. And the steepness is 10.77 and the direction 68.2 degrees. The hiker's decision was to travel along the other blue arrow in the direction 240. He's going downhill. His slope is negative 10.66. Is this the steepest possible downhill for him? No. If he wants the steepest possible downhill, he should probably be going in the direction opposite to grad F, right? But he's not quite doing that. These two blue arrows aren't quite back to back. That's the best I can do. The last page just restates the things I just told you. Some of the things I just told you. So I don't want to spend forever on that last page. Go ahead and go down and look at it if you like. But it restates the fact that grad F represents the steepest possible climb. That's what fact number 1 is saying. The directional derivative achieves its maximum when, or that means its steepest when, grad F and U are perfectly aligned and the hiker decides he's going to travel in the direction of grad F. That's going to be the steepest climb possible. Okay? Good proof for it, but you need it really. The second bullet here is just saying what I told you about the level curve. If the hiker wants to take the steepest path to the top, he needs to take the direction that's perpendicular to the path he's standing on. The contour line he's standing on. Take a perpendicular path, and that will be the steepest to the top. These are all ideas Stewart or get, what's the other one? Larson, Stewart, Thomas. Those guys are like tried and true college textbook 101, you know? And just to comment, I've been calling this CALC 3, meaning third semester CALC. So some people are confused on that. They think it means third year CALC. No, it's third semester CALC. You've done BC, which is pretty much 2 semesters CALC. Some of these ideas are technically considered second semester still. So if you like went off to UCI and you jumped into third semester, which is third quarter there, this might be a little, you might be beyond this. So just know that you might have to take second semester again, depending on the school and what they teach in that second semester. If you are a junior, I really recommend you take a math class next year, something along these lines. We're done with 3-space differentiation. So this is like a really broad overview of everything. Next, we're going to do integration. We're going to find the area, or excuse me, the volume underneath that mountain. So we're talking about how to find the volume under the mountain. And we'll do that next. And then we're going to do a couple first-order linear differential equations called Bernoulli's. And that's the end of the year. You guys are going to take one test on the 3rd. Okay? So June 3rd is our last instructional day. Then we'll do a party on the 4th, sign yearbooks on the 5th, and the seniors will be gone. So that's that.